my name is Luca and welcome to this talk called Simultaneous Diagonalization of Incomplete Matrices and Applications. This is joint work with Jean-Sébastien Coron and Gabor Wiese. As introduction for my talk, I consider the following setting. Let n denote an integer that is at least 2, P and Q rational n by n matrices of full rank, and U1 a rational n by n matrix which is diagonal. Further, according to the following sketch, we denote by W0 and W1 the product matrices P times Q and P times U1 times Q respectively. These are now n by n rational matrices, and we are interested in solving the following problem. Given these two matrices, we aim at revealing the diagonal entries of U1. Now we are not actually interested in computing the matrix U1 itself, but only in revealing its diagonal entries up to permutation. As you will notice, the problem now in the current form has an easy solution, namely bearing in mind that W0 is invertible. Upon computing W0 inverse times W1, we have actually computed a similar matrix, of which now the eigenvalues precisely reveal the diagonal entries of U1. We now take this problem more or less as a base point for a more general study, and our generalization lies in lowering the ranks of P and Q. That means that we denote by lowercase p and lowercase q two integers that are less than n and that refer to the ranks of P and Q respectively. Compared to the previous situation, this now corresponds to having cut a certain number of rows in P and a certain number of columns in Q, in a way that now the product matrix W1 only has size P times Q, whereas beforehand it was of full size n times n. And for this reason we refer to this matrix to be incomplete, whereas note that the matrix U1 is still fully informative. Now, in order to compensate this loss of information in P and Q, we consider multiple equations. That means we denote by capital I a certain index set that ranges from 1 up to t, where t is a fixed integer that counts the number of samples. And in this notation, we then tackle the following more general problem. Given access to these matrices Wi together with the matrix W0, which is P times Q, we aim at revealing the diagonal entries of Ui. Now for an attacker, this means that he would just see the green boxes on this slide, which all have size P times Q. Therefore, if P and Q are reasonably small compared to the size of n, these boxes are rather small. And the attacker then aims at revealing the diagonal entries of the red boxes. In our work, we mainly describe two cases for this problem, and then for each case we devise an algorithm. First, we treat the case where the matrix P is of low rank and the matrix Q is still invertible. And in the second case, we treat the matrices P and Q both to have low rank, and we denote their common rank by lowercase p. Overall, we are interested in solving these problems from the viewpoint of an attacker, which means when least possible information is available to us. Or in other words, we therefore want to find a parameter range for the values p, q, and t that is somehow minimal with respect to a given choice of n. And overall, we are able to devise two heuristic algorithms that perform as follows. In the first case, we are able to lower the rank of P down to a big O of square root n, and the same for the number of input samples T. Now in the second case, when information is lost in P and Q, we lower this rank down to a big O of 2/3 of n, whereas this number of input samples T still behaves as in the first case. Let me now come to giving you key ingredients how to cook up our algorithms. And for this, I will start by the case where the matrix P is of low rank and the matrix Q is invertible. Now, using this invertibility of Q explicitly, it is not difficult to rewrite Wi in this following product form. It is W0 times Zi, where Zi is this similar matrix Q inverse times Ui times Q. And from this, it becomes clear that as soon as we reveal these matrices Zi, we reveal the diagonal entries of Ui upon simultaneous diagonalization. Now, a crucial property of these matrices Zi is that they commute, and this is a key ingredient in our algorithm. Note now that every solution Zi to the previous equation must be written in the following form. Here I am denoting by Yi, a matrix which is a particular solution to that equation, and by S, a matrix of which the columns generate the kernel of W0. Now every such matrix Zi will be a solution to that previous equation. And it is important to note here that the matrices Yi and S are publicly computable from the input data, which leaves us with one single class of variables that in this slide we denote by matrices Xi. Therefore, our goal now is to reveal these matrices Xi and then, upon reconstruction, reveal the diagonal entries of Ui. This is precisely the second step of the algorithm that works by combining the observation that the matrices Zi commute together with their explicit writing. This leads to write down an explicit system of linear equations in which the variables are precisely the entries of these matrices Xi. Now, to simplify notation, let capital E denote the number of equations of that system and by capital V the number of variables. But you can imagine that these values are explicit in the parameters of the problem. Requiring now that there are at least as many equations as variables gives a heuristic way to compute a unique solution to that system. And why this step is heuristic only lies in the fact that we actually deal on generic inputs. And for generic inputs, it is heuristically expected that while adding equations to our system, we do not lose linear independence. Now, the condition that E is at least equal to V is for us a mean to write down an explicit parameter selection. And we show that upon a very simple minimization problem, we derive parameters for P and T that are a big O of square root n. And these simple ideas finish the main overview of the first case. So let us now move to the second case where the information in P and Q is lost simultaneously. That means, according to the following sketch, we obtain product matrices Wi, which are square matrices of size P. Here our idea is to reduce it to the previous case and then use the previous algorithm to reveal the diagonal entries of Ui. Now, in order to do so, we have to augment the matrices Wi to certain P times n matrices, such that an underlying factorization is of the form P times Ui times a certain new matrix Q, which instead of having size n times P, now has size n times n and is invertible. This is precisely the syntax of the previous problem. Therefore, the use of the previous algorithm will reveal on this input the diagonal entries of Ui. Now, in order to do this augmentation step for us, it is enough to compute matrices that in this slide I denote by Vi that satisfy the following property. They are products P times Ui times a certain matrix Q prime, which has fewer columns and such that when augmented to Q, it gives rise to an invertible rational n by n matrix. We explain in our work how to compute such matrices Vi by linear algebra techniques. However, it appears that an attacker needs some extra information to be available beforehand, and that is one main reason why our parameters are not as good as in the previous case. Nevertheless, we lower the rank P down to a big O of 2/3 of n, and the number of input samples to a big O of square root n, just as in the first case. Whereas these problems might at first sight seem very specific, we describe two applications in our work. We first apply our algorithm to an approximate common divisor problem, and more precisely, we here treat the case of the multiprime version based on Chinese remainder samples. Roughly spoken, this problem asks to reveal a secret prime factorization of a public modulus, given access to many, say polynomially many, Chinese remainder samples. And in this context, we are able to use our algorithm to obtain a quadratic improvement on a previously designed algorithm by Coron and Pereira. Second, we apply our algorithms to break an instance of a cryptographic multilinear map scheme. And here we specifically treat the example of CLT13 construction due to Coron, Lepoint, and Tibucci. Back in 2015, this scheme suffered from an attack due to Jean and his collaborators, which exploited several low-level encodings of 0, and our improvement here by the use of our algorithm lies in bringing this bound down, and also here we obtain a quadratic improvement. So I will now pass to more details concerning this first application, that is the Chinese remainder-based approximate common divisor problem, and I would like first to start to recall the statement in its more precise terms. So I denote here by capital N a public modulus, which is composite by several prime numbers pi, of which you can imagine the size so large such that direct factorization of capital N would fail in any efficient way. And together with this public modulus, we consider a set of integers S with the property that every integer in S reduces modulo these primes to a small residue. By this we mean that the representative in the centered modular set is small compared to the size of the prime. And here, with this data in hand, then the problem simply states as follows. Given public access to N and S, we want to derive the complete factorization of N. It is clear that here the number of elements in S plays a big role, as the more elements are available to the attacker, the easier the problem is. And therefore, it is an interesting question to discuss this number as a variable. So, in the algorithm by Coron and Pereira, this cardinality is equal to n plus 1, where here lowercase n refers to the number of prime factors in capital N. Now, by the use of our algorithms, we are able to achieve this improved bound, which gives a quadratic improvement in the input length. Now, in order to make these numbers a little bit more explicit, let me show you the following practical instance. When we consider a public modulus which is composite by 50 prime numbers of roughly 800 bits, and we consider a residue size of roughly 100 bits, then our algorithm needs 19 samples to factor N completely, whereas the old algorithm by Coron and Pereira requires 51 such samples. So this slide here is meant to mainly highlight similarities and differences between the algorithms. On the one side, the algorithm by Coron and Pereira, and on the other side, our improved algorithm. And to convince you that despite many similarities in the construction, they diverge on one main conceptual point. So the cardinality of S being equal to n plus 1 in the algorithm of Coron and Pereira, the set S is given the following representation. Now, from this set S here, an attacker can then publicly compute the following vector. This is a 2 times n dimensional vector, of which the first n entries correspond to certain n elements in the set S, and the last n entries in B correspond to the same n elements multiplied by the remaining scalar in S. In our work, we give this set S a little bit a different representation, and we write its cardinality as p plus t, where p and t are integers that sum up to something less than n. And accordingly, we give the set S the following representation, from which now an attacker can then publicly compute the following vector b. Now, this dimension here is p times t plus 1, and it is exactly this point which is the difference, namely, whereas the dimension in the algorithm of Coron and Pereira is kept fixed with respect to n, it is kept variable in our algorithm, and it is precisely this point which gives us a certain flexibility towards the end to optimize the parameters p and t with respect to n. So let us now see more extensive details of this algorithm, and I mainly divide them up into 3 steps. First, a simple application of the Chinese remainder theorem allows to write b as this following linear combination, where I am denoting by alpha I certain integers, and by b upper index I vectors that are residues of b modulo these primes pi. Now, by design of the problem, these vectors b upper index I are short vectors. And it is not difficult to rephrase the problem as a lattice problem, and more precisely as a lattice problem in which we consider short vectors. Therefore, it is not surprising that the first step of the algorithm is actually a lattice reduction step. More precisely, we can actually do the following. On input b and n, we can use our favorite lattice reduction algorithm, always of course bounded under certain constraints on the parameters, to compute the following data. This is the matrix of which the columns are b upper index I, but only up to right multiplication by an invertible rational and by n matrix Q. And an attacker will actually not know Q explicitly, but we will see that actually this will not hinder him in finding the complete prime factorization of n. Now, the second step is what I here call a diagonalization step, and it is here that our algorithms come into play. So the point here is to rewrite the output of step 1 in matrix products. Namely, we obtain matrix products W0, which is P times Q, and Wi, whenever I is in this index set, which are P times Ui times Q. And here P refers to this P times N matrix, and Ui refers to this diagonal matrix, of which actually the entries are the reductions modulo Pi of certain elements of the set S. This is precisely the syntax of the problems that we're taking interest in, and looking at this more precisely, since the matrix Q is invertible, this is exactly an instance of the first problem. Therefore, the use of the first algorithm on input W0 and Wi will reveal the diagonal entries of Ui. And upon such recovery, it is not difficult to derive the complete prime factorization of n based on simple GCD computations. Now the parameters go inside this second step, and as we have seen previously, the first algorithm supports parameters p and t that are of the order big O of square root n, which gives then this quadratic improvement on the algorithm of Coron and Pereira. To conclude my talk, I'd like to give a main overview of the second application, which is the cryptanalysis of the CLT13 scheme. I first recall that CLT13 refers to this construction of approximate multilinear maps based on the so-called notion of graded encoding schemes. And the hardness of this scheme mainly relies on integer factorization and inversion of Chinese remainder representations. So more generally speaking, multilinear maps have become a very powerful cryptographic primitive in view of their many notable applications, as for instance I list here multi-party Diffie-Hellman key exchange or program obfuscation. Now for CLT13, a total break was already described in 2015 by Jean and his collaborators, and this attack uses a certain number of low-level encodings of 0 to reveal the secret parameters. I denote this number here by big O of n, where lowercase n refers to a certain dimension in which the scheme is embedded. And by the use of our algorithms, we actually managed to bring this bound down to this quadratic improvement, which impacts the cryptanalysis of CLT13 when only a limited number of encodings is available. As for the ideas, they are pretty much the same as previously. Namely, instead of keeping this number of encodings fixed with respect to n, we treat this as variables. And it is exactly this point again which gives us this certain flexibility with respect to the algorithm to optimize the parameters with respect to n. Now with this, I'd like to conclude my talk and thank you very much for your attention.